Make a start. Hello. Yeah. Okay. Just a couple of things. First, a reminder: tomorrow is the deadline for exercise 2 after the lecture. So please submit. There are relatively easy marks. So just submit. It's a good exercise to do. Now, hopefully, it's the first exercise, the marked exercise going round. You can see the marks in the web page. In the web page, there's a link to the marks. You can have a look there. So that, yeah, I think that's probably all the announcements. So what we're going to do today, we will stop briefly talking about the theory of Bayesian inference, and we will try and motivate the need for using numerical methods in Bayesian statistics. Okay, so we hopefully all of you have had a look at the practicals, so you have now a feeling of what this Markov chain Monte Carlo is doing. Okay, so what we will do today is I will do a simple example on the board to motivate, to highlight the problems when we don't have conjugate priors. And then we will start with the next chapter. I think it's chapter 6, hierarchical models, which is the actual important practical method for doing Bayesian statistics. Okay. So, but first things first, so a brief example to motivate the use of MCMC, or at least. This is not in the notes. Okay, so this is an example just to see how this non-conjugacy brings some problems. Our bread and butter, we have data from a Gaussian distribution with unknown mean and precision, sorry. And we know that the conjugate prior P we use. We know that if we use that prior structure, the posterior distribution will be also normal gamma. We've proved that. Now, the problem with this prior structure is that a priori, we are assuming that the precision of the mean is related to the precision, or our knowledge of the precision of the mean is related to the precision of the measurements, right? Which is not necessarily the case. It will not necessarily always be the case. Okay? The mean of any distribution needs not to be related to the precision that we are that we have for measuring that variable. Okay, so it is a bit more natural to have pi of mu and lambda as two independent priors. And we can have, for instance, that prior structure. That probably makes a bit more sense in practice. So if we want to calculate the posterior, will be proportional to the likelihood. We've written the likelihood from this Gaussian example quite a few times. That will be lambda to the n halves exp of minus n times lambda over 2 s squared plus x bar minus mu square obviously there's a times there. So that is the likelihood times the prior. That will be okay. Now, if we want to find the normalizing constant, we will need, can you all see? Yeah, I can probably. If we want to find the normalizing constant, then we will need to integrate these out with respect to both parameters, right? So let's try and do that. Okay, that's what we're going to do. That is our likelihood. That over there. And that is the product of the two priors, okay? So we'll try to integrate that out. And in our case, I can factor out the prior on the mean. Sorry. That will be proportional to and then all the terms involving lambda. Whoop. Interesting. Shouldn't happen. Plus a minus 1. X minus lambda b plus n over 2 s squared plus mu minus x bar square. Okay. As far as I know. Yeah. Okay. Now, the integral with respect to lambda, the second one, looks like a gamma distribution with parameters n halves plus a, and then b plus that factor. So that will be proportional to the integral. It's infinity to infinity x minus p over 2 mu minus m square times that integral, and that integral will be gamma a plus n over 2 over b plus n over 2 mu minus x bar square to the power of a plus n over 2. Okay? Hopefully you'll be able to see that. Okay? And now we're stuck there, right? Because this doesn't really look like any distribution that we know. So this part here looks like a t distribution on mu, and this part here looks like a Gaussian on mu, right? So it's not a simple task to integrate this out. It doesn't look like a known distribution. We can still, if we needed to, do numerical integration here and find that constant. But definitely we will not be able to do anything analytically. Okay? So non-conjugate priors sometimes make more sense than conjugate priors, but that will mean that we will have sometimes a posterior that we will not be able to deal with analytically. Okay? If the dimension of the parameter is small, we can do numerical integration and that will work, but in general, and that's what we will try and motivate in a second, in general, in real life problems, we will have parameters of dimension larger than 2 and 3, or 3, sorry. So numerical integration will not be stable and we need to do something else. And that's where the Markov chain Monte Carlo kicks in. Okay? So is that okay? Any questions so far?
What is it, b plus the last symbol?
Sorry?
Mu minus x bar square.
Yeah. Okay, sorry. Thank you very much. Is that better? Thank you. Okay. So the actual usefulness, I think, in practice of the Bayesian approach is that we can work with what it's called hierarchical models. Okay? And I will try and explain what these hierarchical models are all about. But they are a powerful way of modeling real life situations. Okay? And when we have these kinds of hierarchical models, typically we won't have conjugate priors, and therefore we won't be able to do Bayesian analysis in an analytical way. We'll need numerical methods. So that's the train of thought that we will follow. Okay? Well, hierarchical methods are used or are useful when we have data coming from slightly different populations but are related to each other. And I will try in the next couple of examples to make that idea more or less clear. Okay, so the first example, and that's the first example that you have in your notes, comes from this educational testing data. Okay, so if I'm not wrong, the problem goes like this. We have a test that is taken by all students in a county or in a country or somewhere. So this is the same test that is applied to all students at some point, right? But then some schools will try and use coaching, will try and coach the students in order to perform well in the test, okay? Obviously, the idea of having a test is that you are not supposed to be coached to do the test. You're supposed to be taught to learn something, and the test should reflect that, okay? So what we would like to see is whether coaching has an effect on the results on the test. If that is the case, then probably the test is not very good and needs to be scrapped or something like that, okay? So there are some schools that done specific coaching on their students, and then the difference in marks from those students that were not coached and the students that were coached were recorded, right? So we have 8 schools, and these are the effects, so the difference in marks, in average mark, if you wish, okay? And what we would like to say, is whether there is an effect, whether these numbers here provide evidence that coaching has an effect on the score of the test. Okay. So I believe these are averages. So if there are averages, we can assume that the data is Gaussian, right? So we can use that. The data are Gaussian. Theta I, that will be the mean effect of coaching in the marks. So if theta I is large and positive, then coaching has a positive effect on the marks. If it's large and negative, then it has a bad effect on the marks. And if it's close to 0, then the test is resistant to coaching. Okay, so that's the idea. And just to make things a bit easier at this point, we will assume that the variance is known. And the variance is 36. Okay. So we want to infer basically these means. Okay. We have one observation per school. Okay. And that is important. So we need priors. We have one observation per school, and we have one mean per school, okay? So in principle, we have the same number of observations as the parameters that we have, okay? We need priors on these theta i's. Okay? So the first thing, and that's probably what we can do right now, is to assume that all of these thetas are independent, and if we don't know anything about the thetas, then we can use a flat prior, basically, Jeffreys prior, okay? And if that is the case, if we are assuming that each school is independent, then, for instance, the posterior distribution for the first school will be Gaussian with mean 2839, which is the only observation that we have for that school, and we assume that the variance is known, is 36, okay? So not a problem there, everything analytical, we can do all the calculations that we want. But just out of these, it means that the probability for that mean effect to be larger than 28 is a half, right? And we are assuming that, you know, we are getting the same sort of information from each school. So if we have a look at the data, it doesn't seem that if the theta i's are indeed independent and have the same distribution, having probability 1/2 of being larger than 28 doesn't seem to tally with the data, right? So that doesn't seem like a very good idea, okay? So another extreme would be to assume that all the thetas are the same, okay? So every school is like we're pulling all the schools together, right? So every school is doing basically, if we do that, the same kind of coaching, and the populations in each school are similar, so all of them are just a big sample, Okay? We pull them together. And then we use the same Jeffreys prior on this common parameter now. Okay? If we do that, then the posterior distribution for the common parameter is Gaussian with the mean of all the observations, which is this number here, and variance 36 over the number of observations. Okay? So that is our posterior for all of them, and given that all of them are the same, then that will imply that the probability of the effect in the first school being smaller than 8.82 is half, and probably that's not very good because we know that that effect was 28. So again, that doesn't tally with the data. Okay. So what we need, or what would be useful in this case, would be an intermediate approach. Okay? If we think about the experiment or this data collection, we have the same test, so these results are related somehow. Students are studying the same subject, but we have different or slightly different coaching styles in each school, and each school has different kinds of students probably. So what we can think of is that these effects will not be independent, right? But they will be related somehow, okay? So these effects will come from a population of effects, okay? So what we can say is that each effect is conditionally independent to each other given the population parameters for that effect, okay? Now, each effect in each school will be different, but they will come from the same distribution. Okay? So this will be the mean effect of coaching in the whole population, and that will be the corresponding precision. And out of that population, we will have individual effects. Okay? Again, we are assuming that we don't know mu and tau, again, because that is not observable, actually. We cannot observe the mean effect for all the population, but we can estimate it. So we put priors on those parameters. And that's, again, what makes Bayesian modeling quite powerful in practice. We have this structure here that seems to be sensible from a modeling point of view, but then these parameters are not known. And if they are not known, instead of treating them as constants, as you would do if you were doing a frequentist approach, you use a prior distribution that will allow you to have some measure of uncertainty on these values. Okay. And this is what we call, in general, a hierarchical model. So we have layers that control different parameters and mean different things depending on the population scheme that we have. So on the top level, we have the observations, and we are assuming that these observations are related somehow. In this particular case, they have the same distribution. There are different effects for each school, but they come from the same distribution. So they come from a normal population. But we don't know the characteristics of this population, in this case, this Gaussian distribution. So we need a prior on those characteristics, on those parameters. Okay? So formally, we would write such a model in this way. We have the observations, population of the effects, and the priors on the parameters of that population. Now, that's what I wanted to do this first. If you technically, you can form the joint posterior of all the parameters. Now we have 8 parameters here, as many means as schools that we have. And two new parameters, the parameters of the population of effects, right? So now we have more parameters than observations. But we are linking those parameters through this distribution. And by doing that, we will be able to estimate all of them, right? And the other thing is that when you put together this structure in a joint Bayesian model, this conditioning makes the joint Bayesian model a probability distribution in all the unknown parameters. So what you will have at the end will be a joint distribution, in this case of dimension 10. So that will be a joint distribution on all the theta i's, mu, and tau. And that will depend on the prior parameters of the second layer and the observations, obviously. Okay? I don't know if I have. Yeah. Let me. Yeah. Okay. I will talk a little bit about this and then probably write something in the on the board. So again, that's why I didn't want to. I wanted to do this example first, because we know now that the prior is not conjugate. So if we go back, when we put together all these distributions, we've seen that this structure here, having a Gaussian with unknown mean and unknown precision, and independent priors for the mean and the precision, will lead to a posterior that is non-conjugate, right? And that is just for one of them, one of the effects. So when we put all of them together, we will have a non-conjugate posterior. So we cannot derive any results analytically. Okay, we would need to integrate either numerically or what we are going to do, resort to Markov chain Monte Carlo. This is the key. Now, each one of the effects are correlated. They are conditionally independent in our model, but when we put all the distributions together, they are not independent anymore. They are correlated. Okay? So information about theta I gives us information about mu and tau, and then mu and tau will define the distribution of the individual theta j's. Okay? The parameter that we use for the model, the population model of the effects, the precision, controls how much these theta i's depend on each other. If that precision is high, that means that they are closely distributed together. So you have, or you say that the theta i's are very similar, or if that precision is very small, then they are almost independent, right? And that's why we usually do not fix that parameter, because we don't really know how correlated these parameters are. Or in other hands, if we want, in other words, if we want the data to tell us how closely related these effects are, we need to use a prior on that parameter. Okay? And what I mentioned before, we have more parameters than observations, but given that these observations now, these parameters, are correlated, then we will be able to have a problem, a well-defined problem, a well-defined model in Bayesian terms. Okay? Cool. I probably don't have time. Yeah, I'll do that in the next lecture. So I'll go through the next example just to make sure that we'll try to highlight how this works. Okay. So this is the second example in your notes, and these are failure rates on pumps of power plants. Okay. So we have pumps in a power plant that allegedly are similar. They come from the same manufacturer. They have been given the same maintenance and so on. So they are sort of similar, that they're different, okay? And obviously if the pumps fail, we have a problem. So we would like to understand how these pumps may fail, okay? The rate of failure of the pumps. We gather data on the number of failures of each pump for a determined period of time and record those, okay? So we have now 10 pumps and this number of failures for each one of them, okay? So first thing, we need a model for the data. One probably sensible model is to assume that the data come from a Poisson distribution. And each pump will have a different failure rate, okay? We could assume that all of them have the same failure rate, but hopefully, well, not hopefully, probably, they are not similar enough to be treated as just independent, okay? So they will have, every single one will have a different rate, but we will assume that these rates are related, okay? And one possible prior or one possible model for this failure rate, given that is larger than 0, would be a gamma distribution with parameters alpha and beta. Again, as we have done before, alpha and beta will control the mean and the variance of these failure rates, okay? So if we had information about alpha and beta, we could try and elicit that model. But if we don't, then we need to put priors on these unknown parameters, okay? Again, these parameters are larger than 0. So we can use priors, and this is just an example. You can use any prior that would be sensible in this way. We can assume that alpha is exponential with parameter A, and beta will be gamma with parameters B and C. Okay, so probably, let me just have a quick look, and I can probably write that model. Yes. Yeah, okay. So just to illustrate how a very relatively simple setting will lead to a complex model, let's write down the joint model for this problem. If I can find, yeah. So this is okay. So we have each xi coming from a Poisson distribution with parameter lambda I, and we have 10 of those. We will assume that lambda I comes from a gamma distribution with parameters alpha and beta, and we have the same number of those. And we will have alpha, how did I write? Yeah. Alpha coming from an exponential distribution with parameter A, and beta from a gamma with parameters B and C. Okay? So the likelihood will be, now this is a vector of parameters for data x proportional to the product from I equals 1 to 10, Poisson lambda I to the xi e to the minus lambda I. That is the likelihood, right? The prior structure we are assuming that the lambda i's are gammas, so that will be beta to the power of alpha, gamma alpha, lambda I, alpha minus 1, e minus beta, lambda I, times an exponential in alpha, e to the minus alpha a, and a beta in beta, a gamma in beta. That will be beta to the b minus 1, e minus c beta. Okay? That means that the posterior for all the lambdas, alpha and beta, for observation x, will be proportional to the product of lambda I to the xi e to the minus, minus the sum of the lambda i's times beta and alpha, gamma alpha to the power of n, product of lambda I, alpha minus 1, e minus b, sum of the lambda i's, times minus alpha a, beta to the b minus 1, e minus c beta. Okay. So you could, if you wanted, rearrange it in different ways, but hopefully it's now apparent that this does not look like any known distribution, right? If we wanted to integrate this out with respect to all the parameters, in particular, we would need to integrate this gamma function to the power of n on a, which would be kind of difficult, right? So even for, I'm saying n is 10. Sorry about that. So hopefully now you can have a taste of, even in simple cases, having, is everything okay? Yeah? Having a non-conjugate prior or having a hierarchical structure will lead to posterior distributions that are not analytically tractable. So we need a way of dealing with this in a numerical fashion. Okay. So this is just basically that motivation for thinking about computational methods that we will talk about now, or start to talk about now. So MCMC. What I will do with MCMC, at least at this point, is just I will talk very informally about how it works. You have some proofs on how the actual sampler works, but that's beyond the scope of the course, okay? That won't be examinable. That is just for you to have an idea of how it works. But the important thing is to understand why we're using it and then being able to implement it in practice, okay? So bear with me if you cannot remember too much about your Markov chain or stochastic processes courses. It won't be too difficult, too necessary. Okay, so as we talked about on Tuesday, we are going to use Markov chain Monte Carlo. Monte Carlo means simulation. And simulation is used in practice quite often to solve some problems, okay? One example that you have definitely used quite a few times is if you want to estimate the mean of a distribution and that integral is difficult to solve or it's impossible to solve, one way that you could do that is to simulate from that distribution, get a big sample, and then just average it out, okay? And that will give you an unbiased estimate, actually, of the mean of the distribution. And not only that, you know that the variance of that estimator, again, frequency statistics, is the variance of each observation divided by n, where n is the sample size. So the larger the sample size, the smaller the variance in your estimator. That means the more precise your estimations are, okay? So this is the main idea behind Monte Carlo methods, okay? And the same goes for any characteristic of a distribution that you're interested in, okay? If you want to estimate a probability, and that's what we did on Tuesday, if you have a sample from the distribution and you want to estimate the probability of that random quantity being smaller or equal than certain numbers, say t, you just need to count the number of times in your sample that you had values smaller or equal than that value, than t, and divide that by the sample size, and you will have an estimate of the probability, okay? And again, this estimator is consistent and asymptotically has very small variance, okay? So how does this links with our problem? As I mentioned again on Tuesday, the posterior distribution is proportional to the prior times the likelihood. So we can always get this expression here, the non-normalized posterior, because we will always have the prior, we'll always have the likelihood, so we can always multiply these two functions, however complex they are, okay? But then if we cannot normalize this product, if we cannot find the normalizing constant, then we cannot find means, let alone any probabilities, okay? So what we will do, or what we'll be doing, is to use Markov chain Monte Carlo, employing just the prior and the likelihood to simulate from the posterior distribution. So that means that we don't need to calculate the normalizing constant. Quick reminder of how Markov chains work. So that's the second part of MCMC. Markov chain is a random sequence where the probability of observing the next observation depends only on the current state of the chain, okay? And that's the Markov property, and it's a chain of order 1, okay? So that's probably nothing new for you. The important thing is that under certain regularity conditions, that transition probability will converge to one distribution, okay? And then we say that if after some time t, that sequence has converged to that distribution, then we say that we've reached the stationary distribution by that time, okay? And one thing that we mentioned also on Tuesday is that these samples will not be independent, right? It's a Markov chain, so they will be correlated in time. But in any case, we have a sample from this distribution, so we can use this sample to, again, estimate any characteristic of the stationary distribution. So the idea behind Markov chain Monte Carlo is to construct this transition kernel, this transition probability, in such a way that the stationary distribution is the posterior. Okay? That is the idea. And that's highlighted in your notes. So the key mathematical result is that for any posterior distribution, we can construct a Markov chain with stationary distribution, the target. And the practical result here is that we can do that using standard distributions, right? So we can use distributions we can sample from to reach the stationary distribution. And just, I think that's, yeah, I'll just present these. So this is the Metropolis-Hastings algorithm. This is the key mathematical element that makes sure, that ensures that the chain that we construct converges to the target distribution. Okay? And the way it works is that we select a proposal density, and that proposal density will depend on the current state of the chain. We will generate a proposed value from this density, and then we will keep that proposed value with probability proportional to or equal to this quantity here. So that is the ratio of the target density evaluated at the proposed value and evaluated at the current state of the chain, and then the ratio of the proposal density evaluated at the current state of the chain and at the proposed value. Okay? If we do that, if we propose values and keep them with that probability or reject them with probability 1 minus that, then after some time, the Markov chain emerging from this